Okay, in section 5, we're going to look at the graphs of the other four trig functions, thus the tangent, cotangent, cosecant, and secant. So for tangent, we're going to define it by the unit circle. So if you remember on the unit circle, tangent of x was equal to y over x. Now, the interesting thing about these functions, tangent, cotangent, secant, they all have points where they're undefined. So if I look at the unit circle here, I can figure out where tangent is undefined and define its domain. So since things are undefined, we know when things are 0 in the bottom, we're really looking where the x value is 0. So that would be up here and down here. So those values would be pi over 2 and 3 pi over 2. So generally we say the domain of tangent is all real numbers except x equal to k pi over 2, where k is an odd integer. So whenever you have an odd integer over 2 with a pi and a tangent function, you have an undefined value, because it's going to be infinitely many of these, because you could have 90 as an undefined value, 270, then you go all the way around and you could get another value, and over and over and over again. So you have infinitely many points that are undefined. And if you look here at the graph of tangent, that kind of shows itself because tangent has vertical asymptotes where it is undefined. So you see these gaps in tangent at negative 3 pi over 2, negative pi over 2, or positive 1 pi over 2, 3 pi over 2, and so on and so forth. So wherever you have these undefined values, you make an asymptote. So let's look at some properties of this tangent graph. So the domain, like we talked about, has infinitely many breaks. So we'll say it's all real numbers, x not equal to k pi over 2, where k is an odd integer. The range, remember sine and cosine were negative 1 to 1, but in this case the range goes up and down forever. So it's all real numbers, or in interval notation, negative infinity to infinity. The period of tangent is just one of these waves. So you could think of it between negative half pi and positive half pi, or 1/2 pi and 3/2 pi. But for all these, the period is pi. And in general, if we're going to have a value of tangent with some number in front of x, remember for sine and cosine we divided 2 pi by this number, the period for a tangent function is going to be pi divided by that number, because the typical period is pi. So this graph, like we said, has infinitely many asymptotes, and they're going to occur at those discontinuities, those breaks in the domain. So they'll have asymptotes every k pi over 2, where k is an odd integer. So there are lots of asymptotes. Some examples: negative 5 pi over 2, 3 pi over 2, not in any order by the way, pi over 2, 117 pi over 2. Anything that's an odd number pi over 2 is an asymptote. So the last thing we'll talk about is x-intercepts, because each one of these little periods of tangent, you can see, intersects the axis. And where this is happening, it's basically getting a value of 0. So we're actually looking where the top of our tangent is 0. So we're looking where the y-coordinate is 0. And the y-coordinate is just going to be at 0 and pi and 2 pi and 3 pi. So there's infinitely many intercepts, and they occur at k pi, comma 0, where k is an integer, any integer. So any increment of pi is going to have a x-intercept for tangent. Now these two things are very important, and they will basically occur for all the things we're going to do today. This k pi for integers and this k pi over 2, where k is an odd integer, these will come up over and over and over again in different spots. Sometimes they'll switch, but these things will come up in all the graphs we do today. So let's go and look at cotangent. Now cotangent on the unit circle is a little different, because remember the cotangent of angle x, or angle theta, is x over y. So for things that are undefined for cotangent, we're looking for the y to be undefined, or the y to be 0 to make it undefined. So if we look at this, if I'm looking where the y is 0, we have 1, 0, we have 0, 1, we have -1, 0, and we have 0, -1 on the unit circle. Well, at this point 0 and this point pi, and this point 2 pi again, we have zeros. So if you look at it, we have domain restrictions. In this case, the domain is all real numbers, x not equal to k pi, because it's in increments of pi, where k is an integer. So this is exactly what we had for tangent for its x-intercepts. In this case, it's the domain restrictions. Thus will be the asymptotes for cotangent. And you can see that in its graph. It's got a break at -pi and 0 pi and 1 pi and 2 pi and so on and so forth. So the domain again, all real numbers, x not equal to k pi, where k is an integer. The range is going to go forever, again, so all real numbers. But interestingly enough, this function, the cotangent waves decrease versus increase. So the range will be all real numbers. Period is just one of those waves. So between 0 and pi, pi and 2 pi. So the period is going to be pi. And again, just like tangent, you can adjust that. If I have f of x equal to cotangent of b of x, then the period of this is pi over b. So that'll shrink the period. It'll change where the asymptotes are and all kinds of things like that. So asymptotes for this, the asymptotes are going to be at those domain restrictions. So the asymptotes are going to be every k pi, where k is an integer. And interestingly enough now, like we said, a lot of things switch. If you look at the x-intercepts now, the x-intercepts are where the old asymptotes were for tangent. So the x-intercepts are at k pi over 2 comma 0, where k is an odd integer. Okay, let's look at cosecant. Now, if you recall cosecant was the flip of sine, and sine was y. So if you think about cosecant on the unit circle, it's 1 over y. It's the flip of y. So it's really looking for what values where y is 0 is going to make it undefined. Well, funny enough, that's the exact same thing for cotangent. Cotangent had y on the bottom, so cotangent and cosecant actually have the same domain. So the domain for cosecant is going to be all real numbers, x not equal to k pi, where k is an integer. And if you look at it, it's going to have the same exact asymptotes as the last one. So you can see these breaks in the graph where we have them at -pi and 0 and 1 pi and 2 pi, but a much, much different graph. Instead of getting those waves, we get these almost kind of U-shaped parabolas that alternate in between these asymptotes. And we'll see kind of an interesting feature of cosecant and how it relates to its reciprocal function of sine. So let's go ahead and talk about the parts of it first. So if I talk about the domain is going to be all real numbers, x not equal to k pi, where k is an integer. The range is going to be interesting. It basically is -infinity to -1, because it stops at -1, and then it takes a gap. So we say union, and then it starts up again 1 to infinity. It's basically all the numbers except 1 to -1, and that's how we'd write it. If we want to write it in set builder notation, we could say all real numbers y less than or equal to -1, or y greater than or equal to 1. Both answers are acceptable. The period of a cosecant is 2 pi, because it actually takes 2 of these u's to make one period, because one is facing up and one is facing down. So actually both of those make one period. So just like sine and cosine, if I have cosecant bx, The period of cosecant bx is going to be 2 pi over b. This thing has lots of asymptotes, all the spots where it's undefined, which is equal to k, x equal k pi, where k is an integer. And the x-intercepts are probably the easiest thing because there are no x-intercepts. This thing is always above 1 or below -1, so there are never any x-intercepts. Now, like I mentioned, this is really related to the graph of sine. So I always think about this is if I graph sine, I'm going to graph sine on the same axis. So sine will start at 0, goes up to 1 at pi over 2, back to pi, down to -1 at 3 pi over 2, and back to 2 pi. So if you look at the graph of sine, so this is the graph of f of x equals sine x, you can see that cosecant is really just the outsides of the sine function. And so what I mean by that, I can continue this out. So if I take maybe this portion of the sine graph, I always kind of thought about it, well, if I flip it over its maximum, it kind of flips up in this direction. And then if you have 0, when you flip 0, you get an asymptote, and when you flip 0, you get an asymptote. So kind of an interesting graphical depiction of how sine and its reciprocal function, how their graphs compare. Okay, let's look at the secant function. And just like cosecant, there'll be some similarities to some things we've done before. So remember, the secant is the reciprocal of cosine. Cosine is the x-coordinate, so the secant is the 1 over x on the unit circle. So that was the same as tangent, because tangent was y over x. So this will have the same domain as tangent. All real numbers, x can't equal k pi over 2, where k is an odd integer. So we'll again have lots of breaks in the graph at those odd increments of pi over 2, which is -3 pi over 2, -1 pi over 2, pi over 2, 3 pi over 2. And again, you get these kind of alternating parabolas. One going up, one going down. They're not quite as nice as cosecant because the middle one kind of straddles the y-axis, so still 2 pi, it's just from -½ to 3½ which is a little different. So domain, like we said, all real numbers, x not equal to k pi, where k is an odd integer. Range is going to be the same as cosecant, -∞ to -1, union 1 to infinity. Period, again, we have to have one of those waves going up and one of those waves going down, so it's 2 pi. And again, if I have a function f of x equals secant bx, the period is going to be 2 pi over b. Infinitely many asymptotes at all those breaks in the domain. So that's going to be at k pi over 2, where k is an odd integer. And just like cosecant, there is no x-intercepts, because it's always above and below the line. Now, since secant is the reciprocal of cosine, that same little relationship holds. Remember, cosine starts at the maximum, goes to 0 to the minimum, back to the maximum. So here is one period of cosine, and that same kind of flipping reciprocal relationship exists. If I continue it out, you'll see everywhere cosine is 0, we're getting asymptotes. Everywhere cosine is at its maximum or minimum, we're getting the local max, local min of these little parabolas. So we're going to look at a couple of quick examples of sine and cosine, or I'm sorry, tangent, cotangent, secant, cosecant. We're really going to be dependent on our graphing utility to do a lot of these graphs for us. We're not going to spend as much time as we did sine and cosine on these because they don't have as many applications. But it is a good idea to know what they look like, know what some of the values do in changing the graph. But obviously in all these, I would encourage you to make sure that you are graphing them on Desmos, making sure the graphs are matching up to the answers you get algebraically. So this first one says I have 2 tangent of 2x. So it says state the location of the period and asymptotes. So for the period is typically pi, but we said we're going to divide it by whatever that b is, so that's going to be 2. Now, interestingly enough, for the asymptotes, we can do a similar thing. So the asymptotes typically are x equal k pi over 2, where k is an odd integer. Well, to do these new ones, we'll just divide that by 2 as well. Whatever we do to the period, we're going to do the asymptotes as well. So I'm just going to put another factor of 2 on the bottom, dividing it by 2. Now, if you divide by 2 and flip by the reciprocal, same thing. So this will have asymptotes at k pi over 4, where k is an odd integer. So what that's going to do is that's going to make my asymptotes at 1/4 pi, 3/4 pi, 5/4 pi, etc., etc. So 1/4 pi, I believe, is right here. This is not the best grid, but we'll label it. So that's pi over 4. We'll have 3 pi over 4, which should be slightly after 2 pi over 3, I believe. So there is 3 pi over 4. I could go negative 1 pi over 4, so that should be there. And again, since this is in twelfths, every 3/12 is 1/4, so I'm basically just skipping 6 in between these. So there's negative 1 pi over 4. I could go slightly on the other side here and get negative 3 pi over 4. And I could keep going over and over and over again. Now, generally, this has a x-intercept in between these asymptotes, and that's true here as well. So we have one there in between those two, one here, and one here. Now, the only thing the 2 does in front is it's going to stretch it a bit. So what I'm going to do is, in my tangent ways, I'm just going to make them a little more elongated. So something like this. So there's your graph of tangent. So period is pi over 2, and then the asymptotes are occurring 3 pi, or k pi over 4, where k is an odd integer. All right, let's look at another graph. This one says f of x equal negative cotan x plus 1. So we've got a shift up 1, and we have a flip, but no change in the period or asymptote, so that's really nice. So remember, a typical period for cotangent's 2 pi, and the asymptotes are typically every k pi, where k is an integer. So no changes to that in this case, which makes it nice. So we'll have an asymptote at 0. We'll have an asymptote at pi. We'll have an asymptote over here at 2 pi, at negative pi, and negative 2 pi. Now, the shift up 1 means instead of our value being at the intercept at those odd increments of pi, it'll be shifted up 1. So it's almost like here, in the middle here, in the middle here, and the middle here, and the middle here. So I shifted that up 1 unit. Now, typically, remember, cotangent is going to kind of look something like this, but we flipped it. So we'll make it look something like this. So this is the graph of negative cotangent x plus 1. Again, great idea to check it. Make sure that Desmos is giving us a similar graph. All right, let's look at this next one, which is f of x equals secant half x. Now remember, the typical period for secant is 2 pi. So we're dividing it by that number b in front of x. So 2 pi over 1/2 is 2 pi times the reciprocal 2 over 1, which is going to be 4 pi. So this is going to have a much longer period. Now our typical asymptotes for secant. So they're at x equal k pi over 2, where k is an odd integer. So we're going to divide that by half as well, which is going to be k pi over 2 times 2 over 1, which will be k pi. Now, important to remember that k is still going to be an odd integer. So our asymptotes are going to be at pi and negative pi. And that's all the ones we see on here, because the other ones would be at 3 pi, 5 pi, 7 pi. Basically all we did is we got rid of the 2 on the bottom. So we're not going to see a ton of secant here, but we'll see a little bit. So remember, secant straddles the y-axis, so we'll have it at 1 because it doesn't shift up or anything. So that middle one is like really elongated now. We'll have 1 here. It should go all the way to 3 pi, but we kind of run out of room at 2 pi. It'll eventually go out there and turn back over. Same thing on this side, would go all the way out to 3 pi. But this graph just doesn't show it. So between negative 2 pi and 2 pi, this is the part of the graph that you would see. A little bit more here. But again, there is more. It would continue. It would have the up parabola, the down parabola, and et cetera, et cetera. Okay, let's look at one more. Let's look at a cosecant graph. So cosecant of 2x minus 1. So we do have a shift down of 1, so that'll be interesting. That's going to move those parabolas down 1 unit. Now remember, a period of cosecant typically is 2 pi, but we have this magic b number, so we're going to divide that by 2, so now the period becomes pi. That b number also affects the asymptotes, but in this case, the typical asymptotes are k, pi, where k is an integer. But remember, if we divide it by 2, you just get k pi over 2 where k is an integer, but we have to be careful. K is not an odd integer like typical, k is any integer. So we have 0, we could have half a pi, we could also have 2 over 2 pi, which would be pi. We could also have 3 pi over 2. We could also have 2 pi. We could have 5 pi over 2. So in this case, it was an integer and then we divided it by 2 versus having it the k pi over 2 where k is an odd integer. So we'll have lots and lots of asymptotes, one at 0, one at pi over 2, one at pi, one at 3 pi over 2, one at negative pi over 2, and at negative pi, so on and so forth. Now when I look at my parabolas, remember it usually starts on the up parabola, but instead of starting at 1, it's been shifted down 1, so we'll actually start it down here at 0. So it looks something like that. And then this one down here, it's going to start at negative 2, because typically it starts at negative 1, but it's been shifted down. And so you kind of get this pattern that looks like this. These alternating parabolas in between those asymptotes. So that's just a little bit about the other graphs of our other 4 trig functions. Do remember that we really want to focus on sine and cosine, but these are some pretty neat graphs. They do have some applications, just not as many as sine and cosine. If you do have any questions, please let me know about these graphs.